So we have what? We have that the integral between h and infinity of excz tau zh times t in the z is equal to the integral between h and infinity probability that eta is equal to h equal to z in dz. And again, these are just a dummy variable, the z variable. Okay, so the important one here is h. So let's see what is the shape of what is the analytical form of this footprint for Gaussian processes. When h over sigma is very, very large, which is the domain of validity of this equation, the structure near a large peak is proportional to the covariant function. This is h. So let's assume that at eta 0 is equal to h and the time derivative is equal to 0. So locally to this maximum, when h over sigma is very, very, very large, eta of t is proportional to h times the covariant function divided m0. Okay? And let me remind you that the covariant function is given by the integral between 0 and infinity of s of omega cosine of omega in the omega. And actually, let me take it back. Let's call this z actually. Now I fix a threshold h, which is the one that is very, very large. So all this amplitude is z minus h. And it will be easy now to derive this. This is the footprint that we want to compute, tau zh. But let me do it in a more in a more clear way. Okay, let me draw this this wave in a better way. So we have this is t. So let me write this. Now I fix a very large threshold. Is h over sigma, much greater than 1. Gonna call this is gonna be the level z, the amplitude of the crest, and this process eta t is roughly equal to h times the covariant function divided by m naught. And of course, I'm interested in this time tau 0 and minus tau 0. So this is going to be my footprint, tau zh is equal to 2 times t0. Now I need to find t0. But now what we can do, we can Taylor expand this the covariant function around t equals 0, and what we get? We get h divided by m naught, which multiply phi psi at 0 plus this dot at 0 times t plus the second derivative at 0 times t squared divided by 2 plus blah blah blah. However, we have a local maximum here. This derivative is 0, and this second derivative is going to be less than 0. So I have that eta t is roughly equal to h divided by m0, which multiply. This is, we have seen that is m naught plus the second derivative at 0 divided by 2 times t squared plus blah 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 blah. And since we know that Ct is equal to the integral between 0 and infinity of s of omega cosine of omega t in d omega, the second derivative in t is equal to cosine becomes sine, minus sine becomes minus cosine, so minus integral between 0 and infinity of s of omega, omega squared cosine of omega t in d omega. So this quantity here is equal to minus integral 0 and infinity of omega squared s of omega in d omega. Is right, because this term cancel out. So this is equal to the second order moment, m2. So what I see here, I see that the process nearby a peak can be approximated with the parabolic profile h minus, this is minus, sorry, minus m2 divided by m naught t squared divided by 2. And of course I have to do this 1 minus. So is equal to h, which multiply 1 minus m2 divided by 2 m naught t squared. Okay? And now it will be very easy to derive this expression, because we simply impose that h of 1 minus m2 over m naught t naught squared divided by 2 has to be equal to, I made a mistake here, remember the maximum is z, so the maximum is z, is not h. The maximum is z. Let's see when eta is equal to h, which is this level. And from this equation, we can easily derive that t naught square is equal to what? T naught square is equal to h over z. I bring this on the other side, so I have h over z, and then I do 1 minus, open parenthesis, and then I have the inversion of 2 m naught divided by m2. So let's repeat the calculations. So we see that t naught square is equal to 1 minus h over z, which multiply 2 m naught divided by m2. Because h over z, then this I'll bring it on this other side, and then I'm left with z over h minus 1, I change sign, and that's what I get. So from this, we know that tau zh is equal to 2 times square root of 2 m0 divided by m2 times square root of 1 minus h over z. Nice. So of course, z is greater or equal than h, so this root is well defined, okay? So the argument is always greater or equal than 0. And now we go back to our differential equations, to the integral differential equation. So we have t integral between h and infinity of exc of z times zh in the z equal integral between h and infinity of exponential of minus, probability of eta equal z in dz. And let's plug the expression for Gaussian processes. So we get t times integral h to infinity of exczz 2 times square root of 2m0 divided by m2 1 minus h over z in dz equal integral between h and infinity of 1 over square root of 2 pi m naught e to the minus h squared divided by 2 m z squared, in the z, which I can rewrite as, I can bring these terms outside, and I can bring this term outside, so I'm left with 2 capital T square root of 2 square root of m naught divided by m2 times integral between h and infinity of exczz square root of 1 minus h over z in the z equal 1 over square root of 2 pi square root of m naught integral h to infinity of e to the minus z2 square 2m naught in the z. This is the differential equation that we would like to solve, and we are getting closer, because we just have now to solve this differential equation that can be solved analytically but the exact analytical solution is very cumbersome. You can look at my paper and see the full derivation, but one easy way to see the final results is by doing the following.